Good day. This is Engineer John Richard V. Maginang, and I will be presenting to you my capsule proposal entitled Evaluation of the Mechanical Properties of Intrinsic Self-Healing Asphalt Mixture with Nano-Graphene Oxide. Road plays an important role in the socio-economic growth of every nation. It is commonly used to facilitate the movement and transport of goods and people, and therefore it is very important to assure and deliver high-quality pavement materials. Asphalt, as a material used to paving roads, generally exhibits great benefits when it comes to cost and durability. Thus, improving asphalt properties is vital to withstand high load impact of vehicles and severe weather conditions. The use of asphalt materials was prominent over 5,000 years ago, where it was known to be the derivative of high boiling point of petroleum. Over the past centuries, asphalt has been utilized for waterproofing, caulking, adhesive, and most commonly as a mastic in construction. Asphalt materials plays an important role in road construction. It was termed as a flexible pavement and exhibit extraordinary chemical and physical properties. Generally, an asphalt binder is composed of complex mixture of hydrocarbons of different molecular weight. The American Society of Testing Materials described asphalt as a dark brown to black cementous material in which is commonly of its composition is bitumen, which occur naturally or by processing of petroleum. Different studies has been conducted to cater a more reliable asphalt that can endure large stress from heavy traffic and to provide an easier way to maintain and repair the defects of asphalt pavement. Additional various materials to improve asphalt durability and fatigue resistance has been studied over time. Nanotechnology had become a trend in the improvement and modification of asphalt properties in microscopic scale. Adding nanoparticles normally increases asphalt viscosity and improves its rotting fatigue resistance. Some most commonly used nanomaterials are nanoclay, nanosilica, and nanotubes. The effort in maintaining high quality asphalt pavement had become the greatest challenge in road engineering nowadays. Due to high volume of traffic and erratic weather conditions of the country, pavement deterioration and dilapidation become the greatest problem of the government's Department of Public Works and Highways. Asphalt defects such as potholes, raveling, alligator cracking, rotting, and shoving are due to asphalt's inability to withstand mechanical stresses and poor material quality. To assess this problem, advancement of asphalt technology had emerged, and one of these is nanotechnology on asphalt. Many studies focus on improving the chemical and mechanical properties of asphalt using nanomaterial, and one of the most interesting innovation to asphalt is its self-healing characteristic. Self-healing is a process by which a material tends to repair the damage induced by different type of stresses. According to many studies, self-healing is the asphalt intrinsic response to eliminate damaged cracks and subsequently bring fractional recovery of its original properties. Basically, there are two types of self-healing, namely extrinsic and intrinsic. Extrinsic self-healing are materials that heals through encapsulation of a healing agent like microcapsule within a material matrix which is released after cracking. On the other hand, the intrinsic self-healing is a material's ability to recover its properties in the presence of reversible chemical bonds. Graphene oxide is well known for its unique properties and numerous applications in the field of chemistry, physics, and material science. GO is basically a two-dimensional material obtained from graphene backbone by incorporating several oxygen functionalities. Oxygen and carbon atoms are covalently bonded, resulting into a sp3 hybridized state. It is a nanomaterial that is determined by having an abundant oxygen functional groups on its surface such as epoxy, hydroxyl, and carboxyl group. Its properties are observed to be greater than its original parent graphene resulting into a further potential application. There are many studies about the possible incorporation of graphene oxide in different asphalt mixes. The asphalt with GO exhibits better storage stability and an increase in softening point and viscosity. It improved the fatigue resistance of ordinary asphalt and exhibit an anti-cracking performance and high resistance to rotting and shoving. Though various studies had arose regarding the possible contribution of graphene oxides in the asphalt technology, it is still necessary to further evaluate its ability to promote intrinsic self-healing in asphalt mixes. Furthermore, a comprehensive study and evaluation on the mechanical properties of graphene oxide modified asphalt must be taken into consideration. So, the main objective of this study is to evaluate the mechanical properties and self-healing capability of graphene oxide modified asphalt mixes and how does each factor such as temperature aging and moisture susceptibility, resilient modulus, rotting resistance can be correlated with the intrinsic self-healing capability of geo-modified asphalt. To carry out the objective of the study, here are the materials, methodology, and the design of experiments that will be used in the study. The study will synthesize graphene oxide using Hammer's method. Initially, 2 grams of sodium nitrate will be mixed into 50 ml of sulfuric acid and kept in an ice bath with continuous stirring for 2 hours. 6 grams of potassium permanganate will be added to the suspension and the reaction will be maintained at temperature lower than 15 degrees Celsius. The mixture will then be stirred at 35 degrees Celsius for 2 days and produce a brownish plate. Dilution of the paste with 10 ml water will cause temperature to rise at 98 degrees Celsius and produce a lighter brown color. 200 ml of water will be added. 10 ml of hydrogen peroxide will be added to terminate the reaction, which will be confirmed by the appearance of yellow color. The mixture will be washed and configured with 10% hydrochloric acid and deionized with water several times to achieve neutral pH. Subsequently, the final product will be dried and the GO will be obtained into powdered form. The morphology and chemical structure of GO will be observed using a scanning electron microscope. The study will utilize asphalt binder with 60 to 80 penetration rate, which will be obtained at the LRTK Asphalt Batching Plant in Bulacan. In the preparation of samples, Asphalt 70 will be heated at various temperature ranging from 155 to 170 centigrade. The GO powder will be dried in a vacuum container and will be added in the asphalt binder with content ratio of 0.5% to 1.5% by the weight of the binder. In order for us to determine the storage stability of the GO-modified asphalt, segregation test will be used. The asphalt binder will be poured in an aluminum tube container and stored at a vertical position for 48 hours at 163 degrees temperature. It will be cooled at 7 degrees Celsius for 4 hours and will be divided into 3 segments of equal parts. In accordance with ASTM D36 or known as the standard test method for softening point of bitumen using ring and ball apparatus, the softening point of the bottom and top part will be measured and the softening point difference will be the marker for asphalt storage stability. In order to assess the aging of the geo-modified asphalt, ASTM D2872 or the standard test method for the effect of heat and air on moving film of asphalt, or also known as a rolling thin film oven test, will be used to assess the short-term aging of the asphalt. On the other hand, UV aging tests will be used to assess the long-term aging of the asphalt. The aging time of the test will be set up into 3 to 12 days. In order for us to have a simpler experimentation, factorial design will be used in the study. A 2 to the third factorial design in the determination of the effect of heat and air on moving film of asphalt will be utilized. We are considering three factors, which are the amount of GO in the asphalt mix, the setup duration, and the sample heating temperature. We will set the levels into two, namely for the GO asphalt mix, 0.5 for the low and 1.5 for the high. For setup duration, the low will be 3 days and the high will be 12 days. And for the sample heating temperature, we'll have the low at 155 degrees Celsius and the high at 170 degrees Celsius. We will consider the response as the effect of heat and air on moving film of asphalt. Based from the result of the Minitab analysis, there will be a total of 8 runs in order for us to obtain the necessary equation and the interaction between the factors. In order to assess the surface energy of the GO-modified asphalt mix, Sensil drop method will be used. Probe liquid with known surface energy such as distilled water, glycerol, and methane chloride will be utilized in the experiment. The test specimen, asphalt binder, will be prepared by dripping the glass slide into the hot virgin bitumen and aged bitumen. The slides will be placed in slide shelf and placed in a desiccator before the test. The surface of the aggregate will be smooth using an abrasive paper. It will be washed using alcohol and distilled water and be dried in an oven. After the preparation of the samples, each probe liquid will be dropped on 5 different locations on the surface of the sample, and then the resulting contact angle will be measured. The heating capability of GO-modified asphalt is to be determined by the two-piece heating test or the TPH using the DHR1 hybrid rheometer. In order to assess the rotting resistance of the GO-modified asphalt, rotting potential using asphalt pavement analyzer of a ASHTO TP6303 will be utilized. 8,000 cycle of asphalt pavement analyzer will be done to evaluate the rotting susceptibility of GO-modified asphalt mixture. The test will be conducted at 52 degrees Celsius. The sample size will be utilized is 150 mm diameter by 75 mm height. The pressure hose will be used should be at 700 plus or minus 35 kPa, while the load cylinder pressure was set at 445 plus or minus 22 newtons. The moisture susceptibility of GO-modified asphalt will be assessed using ASTM D4867. The specimen with 62.5 mm thick by 100 mm diameter will be used. It will identify the effect of water on the tensile properties of GO-modified asphalt. It will determine the behavior of the mix under the freeze-thaw cycle as the temperature fluctuated between the maximum of 52 degrees Celsius and 34 degrees Celsius, and with the application of diametrical load at 50 mm per minute. In order for us to identify and evaluate the resilient modulus of GO-modified asphalt, indirect tensile test for resilient modulus of ASTM D4123 will be used. 50 mm thickness by 150 mm diameter sample will be prepared. The samples will be tested at temperatures ranging from 5 degrees to 40 degrees Celsius. The Poisson's ratio condition was assumed to have a value that varies from 0.3 to 0.4 at temperatures from 5 degrees Celsius to 40 degrees Celsius. Again, in order for us to have a simpler experimentation, we will be considered a factorial design of experiment. Specifically, a 2 to the 4 factorial will be used in the determination of the resilient modulus. The 4 factors that we need to consider are the amount of GO in asphalt mix, sample heating temperature, the testing temperature, and the assumed Poisson's ratio. We will have 2 levels for each factor. For the first factor, the low will be at 0.5% and the high will be at 1.5%. Second, the low will be at 155 degrees Celsius and the high will be at 170 degrees Celsius. For the third factor, the low will be at 5 degrees Celsius and the high will be at 40 degrees Celsius. And lastly, for the fourth factor, the low will be at 0.3 and the high will be at 0.4. The response of the factorial design will be the resilient modulus of the geo-modified asphalt. Based from the Minitab analysis, we should consider a 16 runs for the experiment in order for us to obtain the necessary regression equation and the interaction of the factors that affects the resilient modulus of the geo-modified asphalt. So this ends my presentation. Thank you so much for listening and I hope you learned something about my capsule proposal.